Hi, and welcome to the latest edition of ConnectNext. My name is Corey Collings. I'm joined here today with Dr. Scott Hartley. Dr. Hartley is the CEO of Proengin Incorporated, and he is going to talk to us today about detection. There's a lot of different facets to detection. There's some new technology that's coming down the pike in the last couple years to about the last decade. And it really matters across the whole spectrum of hazmat operations, from your initial survey, reconnaissance, identification, all the way through verifying clean post-decon. So without further ado, Scott, floor is yours.
Thank you. So today, I kind of wanted to talk to you, just give you a general introduction of some of the chemical threats and what it entails. And in today's day and age, we are dealing with a multitude of new types of threats or new things that are coming down the pike. So I wanted you to be aware of those and we can talk through those. The majority of where I'm coming from today is I'm not going to give you an introduction on our technology. This is not really a sales call, although I can do that if need be. But for the purpose of this discussion, it's more a general discussion on things you need to be taking into consideration when you are doing trying to detect and making sure that you don't make some of the mistakes that we have all made or some people have learned the hard way to be able to do that. Also, I'm kind of coming today from the standpoint of assuming that you automatically know some things about decontamination as well as detection systems. So I'm not going to go into the differences between different types or families of detectors. I'm really going to talk more from the holistic standpoint of how can we do things better, or how can you things you should be considering to make sure that you're more effective in what you're doing. But first, as far as just talking about the chemical agent spectrum, there's a number of different things that we're dealing with and we'll talk a little bit more about this. And we're going to get to actually make up some chemistry today and do some pretty fun stuff, which is really what I'm enjoying the most, is being able to mix up some stuff and see how they detect it in real life. So as far as some of the things that we're dealing with toxic industrial chemicals, classical warfare agents, and emerging chemical agents with it. Now, the most common threat today, because we aren't getting attacked, are your toxic industrial chemicals. But there are a number of materials that are transported on a daily basis that were used historically as chemical warfare agents. And your chlorines, your phosgenes, some of those materials were used in the early world wars, but now they've been modified or strengthened to become more potent to us as humans with it. In theory, a lot of your chemical warfare agents are just modifications of pesticides and insecticides that are designed to work more against the human body than they are against insects and pests and other things like that. And that's kind of the morphology of how some of these did. But now what you're seeing as far as the emerging chemical agents are some of your pharmaceutical-based agents. So just think about this. 10 years ago, most people didn't even know what fentanyl is. Now people know what fentanyl is probably on a daily or weekly basis. Unfortunately, you're dealing with it. But there also are a number of pharmaceutical agents that are in development or being utilized in these sort of things that can have an impact and can be considered, for all practical purposes, chemical threats or chemical agents to be able to do with that. So we're going to talk a little bit, and we're going to do some examples of those and actually show you today as well. So a couple of things to think about and why this chart is important is just because the materials are present doesn't necessarily mean their threat is as high. So if you had, for example, fentanyl in trace amounts is not really a huge concern for you, but in highly pure versions of it in large concentrations, it can become a threat. Or in some cases, it's even been weaponized. So when we say weaponization of that, it's how you disperse that into like an aerosol so you can impact as much people as possible. Usually to do something that's high purity and high weaponization, it's usually a state actor. So someone that has a large amount of scientists and research and capabilities to make very high pure agents, as well as being able to disperse those agents. So it's a combination of both of those put together. But just because they aren't done on a professional state actor doesn't mean that they can't be harmful. So if you take the sarin Tokyo incident that occurred, the sarin was not also ultimately pure, and it wasn't even distributed very well. It was done in plastic bags. But when you get enough pressure from a subway train, it can disperse it. And so just because something isn't ultra pure doesn't mean that it isn't harmful. And there's a number of things to consider with that. When you're talking with drugs, there are pure drugs, and a lot of drugs are cut. to be able to do that, but that still doesn't mean that they aren't harmful. So you need to take in consideration both the purity and the presence of it. And you get a lot of your toxic industrial chemicals. So your toxic industrial chemicals that are occurring. So every day there's rail cars that are going down, there's semi trucks that have these materials. It's a function of their purity and how they're dispersed that can become a problem. Or sometimes if they're combinations of one chemical to another, that sometimes can create concerns or just unknown aspects of what we're dealing with from it. But understanding, one of the key things is you need to understand first when you understand what you're dealing with, and then understand the nature of the threat associated with it and the concentration levels and other things like that. And that's what we're going to talk about a little bit more today and give you some examples of some of these key principles to be able to do with it. And the state of the material, as we're talking about here, so if they're solids, liquids, or vapors, become important. So if it's a solid, you want to maintain it's not quite as much of a threat to you unless it can get into your respiratory system, or it can go through your skin. A lot of solids don't do that, but some solids can go through your skin. If they're in a liquid or an aerosol version, they become a little bit more harmful to us because they can get into your respiratory tract a little bit easier with it, both the purity and concentration and just kind of the nature of the chemical itself. Some chemicals are persistent, some evaporate very quickly. Some, when they're combined with air or with humidity in air, can create problems for us. So there's a number of things to consider as part of your overall detection capability and the threat associated with it that we were going to talk about today. So kind of your detection 101, every situation is different and unique. And so kind of the way that I like to talk about it is having a good process is ultimately the most important thing. So when I say a good process, it's going through and starting from the things that you know, and then going to the things that you don't know. So a lot of hazmat calls when they're being made, you'll know probably half, if not more of the time, what you're dealing with. So you're starting from the standpoint, at least what you know what the chemical is. But from a detection standpoint, you need to make sure that you're selecting the right detection capability for what you're trying to detect. And that's one of the first important things to do. There are a number of tools that are out there to let you do that. So one of them, and we're going to talk about it more, is the chemical companion software that exists. It was developed by the government, and it has a huge amount, thousands of chemicals in it. And it has a lot of information in there as far as if you know what the chemical is, and you can select what detectors are able to detect it. So it'll tell you upfront what's effective or not. And so one of the most important things is you just don't want to go just jump right into a situation without first doing some situational assessment and selecting the right types of detectors for the situation that you're dealing with. If you bring the wrong detector or detectors into a situation that either don't have the capability or can't do it at the concentration that you're dealing with or aren't operationally relevant, that information has some value, but it's not as important as it could be. So the selection of the right detectors when you're going into the situation becomes a very important aspect, and one of the things we're going to talk about in more details. And the other thing is knowing your detector system. So a lot of times detectors are told, and a lot of times when people sell detectors, they tell you what it can do. What the problem is, they don't tell you a lot of times what it can't do, or where it doesn't have good capabilities, or where it's weak, or where it maybe takes a long time to detect. So knowing all these things become important for your overall holistic approach to detection to be able to do that. So what are some of the key principles that you want to know for it? And we're going to talk in a lot of detail about this. Is it operationally relevant? So when I say operationally relevant, does the detection capability match the threat profile that you're faced up against? So are you selecting the right tools to go in there that will be able to detect the agents to be able to do that? Another thing is your turn on time. So some detectors, if I turn them on right now, they'll probably be good to go, accurate, and maybe tomorrow. And if you're in the middle of a situation and you don't have 24 hours to get to that point, then it might be say, hey, I need to select a different detector. So just because it's turned on doesn't mean it's 100% functioning. Other detectors, you can turn them on, they're up in 30 seconds or a minute, and they're good to go. But you have to understand what detectors do that and what detectors don't do that. And that's one of your key mistakes that we've seen. People selecting or thinking that a detector, just because it's on and it's operating, that it's operating to its optimal performance. That isn't always the case. So to be careful with that and to understand there. The importance of sample rate and response time. So different detectors have different ability to respond. So when they're seeing the chemical, it takes a while for them to tell you, hey, I'm actually seeing it. Or how quickly they're sampling. So why does sampling become important? So if I'm going in this whole room and I don't know exactly where my thread is and I'm walking around there, if it takes my detector 30 seconds for it to see and I'm walking around there at a normal pace, what are the chances I'm going to miss something? Pretty high. Now, if you have a sample of a detector, like for example, our detector it samples every 2 seconds. So it's telling you what went through the detector over the last 2 seconds. I can walk a little bit faster than I can if I'm walking through a detector that it takes 30 seconds, right? Just it's common sense. But one of the things is when you're in an emergency environment, sometimes you don't think through that, or you aren't considering that. Just because the detector's on, you think, oh, it's operating, it's going to sense it. That's not always the case. The other thing you have to take into consideration, and we're going to show you a direct example of this, is the nature of some of the chemicals. Some of the chemicals are heavier than air. So what does that mean? They're going to be down towards the ground. So if you're sampling up here and your threat's down there, what's your chance of you're missing it? Well, depending on what the concentration is, if it's a lot heavier than air, it's going to take a large amount of concentration for it to come up to the point where you're holding your detector. So understanding your threat and then how you're detecting becomes important, right? So if you know it's a heavier than air threat, that means that you should have your detectors as close to the ground as possible, or have it on something that allows you to, hold it down. Some detectors actually have like a little metal rod that you can hold it on or something to bring it closer to the surface, so it doesn't require you to have to bend down to be able to do that. Cross sensitivity. So cross sensitivity is when one detector tells you something, but it's actually telling you something different because it has sensitivity. Even though it's not what it's primarily designed to detect, it has some sensitivity to it. So what does that mean? It's sometimes your detector can trigger or say there's a threat when it's actually cross-sensitive to something else. And so you need to know that going in front of your threat profile. So if you know what the material is, it's important for you when you're bringing one of the detectors that you know has cross-sensitivity in there to know that, hey, it may detect on this other channel before it detects on the one that I really care about. So you need to understand those ahead of time. And that's where just a quick search or before you go into the building to educate yourself can pay immediate dividends for it. A lot of times when we have our detectors go off, it's like, oh, you're immediately worried. But if you didn't, if you knew ahead of time, okay, it's cross sensitive on this channel, but this one isn't, then you know that information ahead of time and then you can react accordingly. If you wait until it already goes off and then to try and figure that out, it's not always the best because you're now in a situation where you're getting people that can react and do things that you may not want to do. So having that information can be very valuable ahead of time. And then your accuracy. So one of the things with certain detection technologies is that there can be false positives or false negatives. So that's around cross sensitivity and accuracy can tie into each other, but depending on the nature of the detector system. So there are detectors, IMS detectors, for example, that are molecular weight based. And so what can happen is that there's more than one material that can have the same molecular weight. So sometimes it could tell you that it's measuring that molecular weight accurately, but it may not be the material that it's showing you to be. And so that's why it becomes important to be able to do that. There have been a couple of well-known things where something was flagging as a nerve agent, for example, and it was not. It was a chemical cleaning solution or other things like that. So it's important for you to understand where there are some false positives or false negatives associated with some of your detector systems. So therefore you can make wise decisions or bring in another detector that will give you a positive or negative indication of it. For example, our detector, for example, the AP4C, it can detect phosphorus. So a majority, pretty much all of your nerve agents are organophosphate-based materials, so organic compounds containing phosphorus. So if you're getting a hit, for example, on IMS, and you bring in the AP4C and it doesn't hit on phosphorus, then you know it's most likely not an organophosphate, right? So because you can get that verification from multiple detectors, you can get an indication of, is this truly happening or not? But if it's telling you, IMS is telling you that it's hitting on a nerve agent, you come here and you do get the phosphorus, then you get a pretty high correlation that most likely you are dealing with a nerve agent or organophosphate-based material system. So we talked about operational relevance to go into there. And so one of the important things is based upon the threat that you're seeing, where most your detectors, the area that you're most concerned about as far as trying to make useful information is what we call operational relevance. You can call it different things, but really what you want to do is you ideally select the detector that gives you information from below your permissible exposure levels up through your ideal H. And so why is that important? Well, if your detector doesn't detect till above ideal H, is that useful information? Of course. Is it useful information if you don't have proper protective material on? Well, it's going to be a bad day for you, right? So you don't want to do that, obviously. You ideally want to start to detect below where it starts to be a concern to us as humans that can have an impact on us. In many cases, you may not get that. You might not always have that ability, but especially if you know exactly what it is you're dealing with, that's one advantage of using software like the chemical companion software that's free to you, is that it'll allow you to select the detectors that give you as much information in that operational relevance, or let you know that your preferred detectors, if they have operational relevance for the threat that you're dealing with right here. And why it becomes important is you're in the range of interest is to be able to do this. And also, I mean, you as first responders, one of the things that you're trying to do is to assess the situation and figure out, hey, do I have to evacuate a certain amount of area? You're trying to figure out, where's my safe area? Where is it not? Is the threat profile growing? And so for you to be able to do that, you want to have the detector or detectors chosen that give you the information that you need in those operational ranges, right? So below your PL is important. If your detection, however, can only go in PL and can't even reach to PL, like if it's below PL, doesn't reach it, or just barely gets to PL, that becomes important, but maybe not fully useful as a detector that can take you from below to ideal H. And so one of the challenges is each detector system has different operational relevance for different chemicals because the threat profile is different. The way that the detector works is different. So one of the things why this becomes important, especially if you have the luxury of knowing what it is that you're dealing with before you get there, is you can select those detectors that will give you, that are in your arsenal, that you have available to you, that give you the most operational relevancy for that threat. Also making sure that you're taking consideration the fact that what's my response time and the nature of the threat. So one of the biggest concerns that you have is the threat's present. You're going through the building, but you're going either too fast or you aren't detecting the right areas and you aren't detecting anything, but yet the threat's still there. And that's where it starts becoming scary because you're going through and you're getting no information that it is, but the threat is still there, right? So that's why sometimes with detection, you can get a false sense of security going through, hey, I'm looking for this, I didn't find anything, or I did and it's below PL, I don't have to worry about it. Well, the problem is, are you really doing the right thing? So understanding where the source of the material is coming from, for example, and then doing assessment, but also understanding the nature of the threat that we're going to are all kind of important for what you're dealing with it. And then just to kind of give you an example, and we're going to show you some different things. So this is just a screen capture from the chemical companion software. So in this case, we've chosen a common material, which is your ammonium gas. And we checked, since I'm able to pick what I want, I chose something from the AP4C, the shameless plug here. But so let's say you have 4 bars on your hydrogen nitrogen, because that's what hydrogen nitrogen is in your ammonium material. And you can see here your relevance. So where your PEL is and your ideal H, and you can see the relevance on how many bars and what that correlates to. So why that becomes operationally important is I know that I'm below ideal H, fairly significant, about halfway, but I am above PEL. So I have information that I can then use to assess what my threat level is. I can also use that I can put in 1 bar and see whether if it's below where my PEL is, then I can use that to help set up where my area, where your safe zone to your gray zone or other, depending on the way that you handle it. So this is a huge asset for you. And there's more than just our detector in there. We had nothing to do with the creation of the software. We just happened to be included in there. But for all your detector systems, it'll tell you, is it detectable? You can select it. And then this is the display that's on our device, but it'll have the display or similar information to other detectors. And you can use that to make wise and relevant decisions. So next what we're going to do is we're going to go into a couple examples where we're going to create some different chemicals and look at the response of detectors and talk to you through some of the principles that we had talked about today.
Thanks, Scott. That
Sure.
was great. I think one of the key points that you had hit on earlier when we were discussing this earlier was that there's not. It's more important to know what your detector can't do versus knowing what your detector can do. There's not one golden bullet detector out there that will do everything. Everything in your hazmat call, every chemical, every situation. You really need a variety of different detectors. You need to understand the capabilities and limitations of each, and then most importantly, really be well trained and know how to operate those detectors in a practical environment. So what Scott and I have been doing before this, and we'll do a little bit afterwards, is just some experimenting with different chemicals, a number of different simulants, and even some precursor agents to some of these chemistries that we're looking for. And we'll actually try to give you guys a real world demonstration of how these chemicals behave on the particular detectors that we're working with here today.
The first gas that we're able to detect or look at is hydrogen sulfide. It is a toxic and flammable gas with the characteristics of smell of rotten eggs. We chose this gas first because it allows us to demonstrate some of the topics we discussed in the presentation. A hydrogen sulfide reaction can occur from a number of sources, so that it can be purposely or accidentally created using a number of common materials. It requires an acid source, typically hydrochloric or sulfuric acid, mixed with metal polysulfide sources to create hydrogen sulfide. For this example, we created a relatively weak reaction, but we are still able to demonstrate some of the important aspects of detection. First of all, the gas is colorless, so if the source was hidden, our eyes wouldn't be able to detect it. The vapor you are seeing is a reaction with the raw materials and the humidity in the air. For the AP4C detector, it will detect hydrogen sulfide in the sulfur channel, which is designated as S on the meter. Hydrogen sulfide gas is heavier than air, so this must be considered when detecting it. As you can see in the video, as the detector is moved above the sample, the gas concentration is reduced, but as it is brought closer to the sample, the detected concentration increases. This is an important consideration to take into effect when you're trying to detect it. If you're holding your detector very high up in the air and the source is down low, you may not be able to detect it, and this can be seen directly from it. We're also agitating the sample slightly due to the fact that we have a small concentration of a relatively weak concentration of the hydrogen sulfide, so that it allows the reaction to occur and for us to see it. Our noses are able to detect hydrogen sulfide since it has a strong rotten egg smell due to the sulfur. However, odor fatigue has been seen with hydrogen sulfide beginning as low as 50 parts per million, making it impossible to smell the distinctive smell. Odor paralysis sets in at about 100 parts per million, making it impossible to smell any smells. A hydrogen sulfide reaction can occur from any number of sources. It requires an acid source, typically hydrochloric acid or sulfuric acid, mixed with polysulfide. So the metal polysulfide sources range from detergents such as laundry detergents and dandruff shampoos, to pesticides and insecticides like lime sulfur, to home improvement products like spackling paste, latex paints, and oil-based paints. As far as detection is concerned, there are a number of detectors that are able to detect hydrogen sulfide with it. These include detectors such as PIDs, colorimetric tubes, combustible gas indicators, E-cells, and flame spectroscopy such as the AP4C. Each of these has different response times as well as detection levels as far as low to high. Again, taking consideration what are the dynamic ranges that you're most interested in, usually below TPEL to IDLH. So it's important to select the right detector that helps with that range for it. In this case, we're also using a 5-gas meter to be able to detect it. As you can see, again, we're demonstrating the fact of that the material is heavier than air. So as you're detecting above it, you can't really see it, but when you put it directly into the source, since it's heavier than gas, it'll come out of the beaker and want to go down towards the ground, to the surface of it to be able to do that. Now, we are operating here in a vent hood. So because of the vent hood, you will have some gas that tends to go upward more so than it would be in a normal type of environment where there's no uplift of air in the device. The AP4C detector starts to detect around 0.076 parts per million and can go up to around 2 parts per million in the high end. So each of the bar levels indicate a range of response, but the total dynamic range is from around that 0.076 to around 1.9. The response time is 2 seconds for the detector. So every 2 seconds, the detector is updating exactly information regarding what went through that detector over the last 2 seconds. With a PID, the low end of the detection is around 0.33 parts per million, and it can go up to around 1,500 parts per million with it, and the response time is about 3 seconds. So you're kind of seeing in this case that we are able to, the response times, you can see they're relatively close, with the PID moving a little bit slower, but the detection levels are about the same, with AP4C being more sensitive than the PID is able to be done. But both are indicating both the fact that the gas is heavier than air, as well as its presence in there to be able to do that. The next material we chose is fentanyl. For this example, we are using fentanyl which has been dissolved in methanol. This specific sample has a concentration of 1 milligram per milliliter. In this specific case, we are starting out with a simple pour of materials onto a sample plate. You can see when the fentanyl is poured out that enough material is aerosolized that the AP4C detector goes off on the hydrogen-nitrogen channel. A lot of pharmaceutical-based agents, including opioid families, have hydrogen-nitrogen bonds which are detectable via flame spectroscopy. It is interesting to note that even a simple mixture with a small amount of fentanyl in solution produced enough of an aerosol that it was able to be detected, even though a small amount of material was just poured out. As the aerosol dissipates into the air, the detector quickly goes back to zero. In some cases, a liquid may not be off-gassing or have sufficient physical movement in order to vaporize or aerosolize. In these cases, a sample may be required. The AP4C kit comes with an S4PE liquid solid sampler and sampling strips. A sampling strip is placed on the end of the S4PE and is used to collect some of the methanol-fentanyl mixture. When the button on the sampler is pressed, the heating process begins as indicated by the red light. In this case, the S4PE cannot reach the temperature needed to vaporize the fentanyl, and no trigger is observed on the detector. This was shown to demonstrate the importance of understanding the physical properties of the material you are trying to detect. There's fentanyl on the strip, the S4PE heater is working, and the detector is working properly. However, what is missing is sufficient temperature needed to vaporize the fentanyl. Later this year, we will be introducing a new heater which will have a higher temperature range and higher temperature sampling scrapers needed for the latest generation pharmaceutical-based agents, as well as fourth generation agents, and this will also have additional applicability to higher temperature ticks and TIMs. To demonstrate what would happen if you had the higher temperature heater, we have simulated this by placing a sampling plate on top of a hot plate which heats to around 400 degrees Fahrenheit. We have switched to solid fentanyl, which has been mixed or cut with acetaminophen. Due to the power of fentanyl, street versions of fentanyl are often cut with other materials. This can sometimes make the identification of these materials harder, especially for library-based detection systems, since you're dealing simultaneously with more than one material. Since the hot plate has been on for a while, the melting and vaporization of the fentanyl acetaminophen mixture is almost instantaneous. If this was occurring from room temperature, the vaporization would have taken longer to occur. The AP4C is able to detect these materials as soon as they are introduced into the detector. Like with the liquid material, they are detected on the hydrogen-nitrogen channel. Malathion is organophosphate insecticide
that is commonly used to control mosquitoes and a variety of insects that attack fruits, vegetables, landscaping plants, and shrubs. It is also used indoors on pets to control ticks and insects. Since most nerve agents utilize organophosphate-based chemistry, we are using this as a simulant for nerve agent. Most nerve agents are actually modified versions of insecticides or pesticides and were modified specifically to be more effective against humans. The chemical structure of Malathion is C10H19O6PS2, which means that it's capable of triggering on both the phosphorus and sulfur channels of the AP4C due to the presence of both phosphorus and sulfur in the structure. Most organophosphate insecticides and pesticides are designed to be persistent agents, meaning these don't off-gas very much and tend to be oily liquids that readily stick to materials and don't often easily wash off in the rain. As such, we are using the S4PE and taking a sample of the material and will heat it off. Note how the detector first triggers on the phosphorus channel, and only when the phosphorus channel is almost maxed out, it starts to trigger on the sulfur channel. This is similar to how a lot of detectors work, where there's different trigger levels for different channels. The AP4C has different trigger levels for each channel, and the phosphorus channel doesn't start to trigger around 2 parts per billion, while the sulfur channel doesn't trigger to around 76 parts per billion. This demonstrates the importance of understanding trigger levels and ranges for each of the detectors you're using.
In this video, we use 2-chloroethyl ethyl sulfide, or CES, as a mustard agent simulant. This material has a fairly high vapor pressure, so as you can see, it immediately triggers on the sulfur, or HD channel, of the detector. This material, like mustard, is also a persistent chemical, so repeated sampling will get repeated results. We'll also demonstrate in this clip how we can use detection to verify decontamination. In this case, we use a FiberTech wipe as it was designed for the decontamination of chemical warfare agents to include mustard agent. This is just a physical removal step. We're not fundamentally changing the structure of this chemical in any way. We're simply absorbing it into the wipe and removing it from the coupon to be sampled. And because of the fast response of this detector and the high sensitivity of this detector on the sulfur channel, we are able with a high degree of confidence to verify very quickly that our surface has been fully decontaminated. In this next clip, we're going to use DMMP, or dimethyl methylphosphonate. DMMP is an organophosphorus compound often used as a simulant for G-series nerve agent. It is a highly volatile compound. It off-gas quite a bit, so it works well with demonstrating various detectors' ability to pick up organophosphates or phosphonate compounds. In this example, we use a basic paper towel to wipe and remove as much of this compound as possible from the coupon. And although the coupon appears to be visually clean, we can demonstrate, in fact, there is residual contamination on the coupon. Again, this is a very volatile substance, and the detector we're using has a very high sensitivity to the phosphorus channel, so we are getting some indication that there is still contamination on this coupon. Next, we're going to show how even putting a small amount of DMMP back on this surface, you'll begin to see a rise in the levels picked up by the detector. However, chemical and physical properties of the chemical matter. By wiping again and spreading the surface area, we're increasing the volatility of the DMMP, which is going to correspond to a rise you'll see in the detector. So I want to thank Dr. Hartley for that excellent presentation on some of the ins and outs of air monitoring, and especially some of the capabilities of the AP4C. Had a great time going through some of these demonstrations. So I just want to let everybody know that's watching this, we have decided to move our free educational series to YouTube. So if you're interested in receiving updates and following this series, make sure that you subscribe to this channel, because that's where this will be hosted. As well, if you have a topic, technology, new product you're interested in profiling as part of one of these series, go ahead and contact us at training@firstlinetech.com. And thank you everybody for watching. I'll see you next time.